starting video 2 for section 5.3, and we're picking up on number 7. The instructions for this section are simply to evaluate the integral. And so, as we discussed, to evaluate an integral, all you have to do is find the antiderivative of the function, and so in this case it's just the function 7. So the antiderivative of 7 is 7x, which then we're going to evaluate, so we use the evaluation bar, from 1 to 3, which gives me 7 times 1, and then we subtract 7 evaluated at 3. So we evaluated at the top bound, the upper bound, whatever's written up here, and then we evaluated the lower bound, and we subtract the two. So that gives me 7 minus 21, so the answer is negative 14. And that's it. If we wanted to see graphically what just happened, we have the function of 7, which is up here. So here's the x-axis, here's the y-axis. Here's 7. And so we're integrating not from 1 to 3, which is going this direction. So we'd have positive height and positive height, which would be 7 times 3, or 7 times 2, excuse me. So that would be 14. This one is actually, if you notice, we're going from 3 to 1. So what the implication there is that now my widths are going to be negative. So that's more of a negative 2 for the width and a positive 7. And that's why we get negative 14. Okay, so the rest of these we're just going to evaluate using the rules. So on number 8, the function is 5x. And so if you want, we can apply the constant multiple rule. For the most part, I usually don't worry about this, or I just do it in my head. But on this first one, let's do it. So we can rewrite it as 5 from 0 to 2 x dx. So now we're just finding the antiderivative of x. So that would be 1/2 x squared, but we're multiplying by 5. So that really makes the integral simply 5/2 x squared. Evaluated from 0 to 2, which when I plug in 2 is going to get me 5/2 times 4 minus 5/2 times plug in 0, which gives me 10. So the answer to the question is 10. Number 9. Some of you expressed some concern about this one in class, and that's because we're looking at x over 8 as kind of as like a quotient rule, or it's as a fraction. I don't really look at it as a variable divided by 8. I'm going to rewrite the problem. Normally I'll just do this in my head, but for this, I'm going to rewrite the problem to be 1/8 x dx. So we know that the antiderivative, and again, I can visualize that I can pull the 1/8 out if I want. So essentially in my head what I'm going to do is I'm just going to see the x, and the antiderivative of x is 1/2 x squared, but then I have the 1/8. So that's going to give me 1/16 x squared, which I'm now going to evaluate at 3 and at 5. So the upper bound first, I get 5 squared, which is 25. So I get 25/16 minus, putting in 3, I get 3 squared. So I get minus 9/16. So 25 minus 9 is going to be, what, 16? 16ths. Oh, hello. Had a little moment there. So it looks like the answer is 1. Moving on, the antiderivative of 2t minus 3 is t squared minus 3t, evaluated from 0 to 2. So I get 4 minus 6, plugging in the 2 squared minus 3 times 2, minus, plug in 0, and I get 0. So I get 4 minus 6 is negative 2. Okay. So continuing, the antiderivative of t is 1/2 t squared minus the antiderivative of root 2 is that's just a constant. So then that would give us root 2 t. Check it if you're not seeing it. The derivative of the square root of 2 times t would just be the square root of 2. Evaluated now from 0 to the square root of 2. So I get 1/2 the square root of 2 squared minus the square root of 2 times the square root of 2. So that's me plugging in the square root of 2. Now I subtract, plug in 0, and I just get 0. Square root of 2 squared is 2. 1/2 times 2 is 1. Minus root 2 times root 2 is 2. And the answer is -1. Number 12. Again, I have the z over 2 issue. So in my head, I'm not going to rewrite it this time. I'm just going to see it as 1/2 z. So the antiderivative of 1 is z, and plus the antiderivative of 1/2 z. I'm going to do the z first, which gives me z squared, but it'd be 1/2 z squared. So I need to multiply that 1/2 by the 1/2 I have in the problem. So that gives me 1/4. So check that. The 2 comes down. 2/4 is 1/2, which is what I have, and I get z to the first. So for those of you who really didn't like that, maybe it would make sense to think of doing these integrals separately. So the integral of this part of it would be the integral of 1/2 z, which would be this. So now we do the antiderivative of the z, which is 1/2 z squared times the half. So that's where we got the 1/4. Evaluated from 1 to 2. Plug in 1, I get 1 plus 1 squared, so that's 1/4, minus, put it in parentheses, 2 plus 2 squared is 4, 1/4 of 4 is 1. So I get 1 plus 1/4, which is 5/4, minus 3. So I get 5/4 minus 12/4, which is -7/4. Okay, moving on. Number 13 and 14 are ones we're not going to be able to do by hand because, at least for the time being, we have decided to skip. We skipped, when we did the derivatives, we skipped learning the function that has this as its derivative. So then the antiderivative is obviously difficult. So why don't we, I'm not going to do this one for you, but why don't you just do these on your calculator? So do your calculator on this one. Got tired of the red, so I switched to purple. Alright. So now we get to 15, and again, just because it's not a polynomial, it doesn't change the rules. We find the antiderivative of e to the x, which is the easy one. It's e to the x. So the derivative of e to the x is e to the x, so we've got it. Evaluate from 0 to 2. So I get e squared minus e to the 0. E squared minus e to the 0 is 1. So I'm fine with this as an answer. We don't need to go to a decimal or anything like that. Number 16. Alright, let's take a look at 16. First of all, I don't really like this dx sitting on top here. It sort of muddies up the water of what the function is for me. So what I would do in this question, and I'm going to probably write this twice, I would first think of it as asking this question. 3 over x plus 1, and then times dx. And that's fine, because if I were to multiply these two things together, which is what we're saying right here, then the way we multiply fractions is we do 3 times dx, x plus 1 times 1, and so we're back here. So anytime I have this issue with the dx, I just prefer it written off to the side. Okay, so that's the first rewriting of it. But now I also want to, this 3 right here is bothering me. So I'm going to look at this function as 3 times 1 over x plus 1, which is the same thing. Hopefully you see that. 3 times 1, again with the multiplying, 3 times 1 and 1 times x plus 1. So if I'm going to look at the function as this, then the first thing I'm going to do is I'm going to use the constant multiple rule, and I'm going to pull that 3 out of the function. So now I'm going to look at it as 3 times the integral from 0 to 3 of 1 over x plus 1. Okay, so now I got to find the antiderivative of x plus 1. So one thought about that might be to use some sort of power rule. I'm kind of running out of room, so I'm going to doodle over here. So I could think about the function as being, the derivative is x plus 1 to the negative 1. And so then we can use the reverse of the power rule to try to get to y equals. So I'm going to add 1 to negative 1, which gives me x plus 1 to the 0, which is 1. Which clearly, if I take the derivative of 1, I get 0, not what I started with. So long story short, this power rule, it's not working on this problem. And as we discussed back when we did antiderivatives for the first time, that needs to be the thing that triggers your memory that this one is acting weird. This isn't going to work. And so now we need to start thinking about the other, various non-polynomial rules we learned for derivatives. And if you check them all and you think about them all, eventually you're going to run across the natural log of x. If you recall, the derivative of the natural log of x was 1 over x. So the antiderivative of 1 over x is the natural log of x. So that means my theory here is that the answer is going to be the antiderivative of this is going to be the natural log of x plus 1. Now let's check it. The derivative says 1 over x plus 1, but we'd have to do a chain rule. But the derivative of x plus 1 is just 1, so we don't have any issues. So one more time, the derivative of natural log of x plus 1 would be 1 over x plus 1, which is what we have. And then don't forget we had the 3 out front. I'm going to put a little asterisk by this one, at least mentally, that later on, not too far in the future, we're going to slightly alter the answer to this, but we're not going to worry about it on this first lesson. Okay, so there's my antiderivative. The rest is just evaluation. So I get 3 natural log of plug in 3, so 3 natural log of 4, minus 3 natural log of plug 0 in, and I get 1. Some of you are probably going to call that the answer, but if we stop for a second and look at this, the natural log of 1 is asking you e to what power is 1. The natural log of 1 is 0. So 3 times 0 is 0. So my answer to this is actually simply 3 times the natural log of 4. Okay, so before I stop this video, I want you to go back now and look at number 13. Oh look, I just realized I wrote 13 really poorly. I put the dx like they did, and then I put the dx on the side as well. Okay, so one might think, well, wait a minute, if we could do natural log with number 16, then number 13 looks pretty darn similar to that problem. So the question is, well, why wouldn't the answer to the antiderivative then just be the natural log of 1 plus x squared? Well, let's try it. So let's say that the antiderivative is the natural log of 1 plus x squared. Okay, so then let's check that. So the derivative of that would be 1 over 1 plus x squared. But now I've got a chain rule, which I did here as well, but the difference is when I took the derivative of x plus 1, it was just times 1. So it didn't make there was no issue. But here, the derivative would leave us with a 2x. So that would mean I have a 2x where I don't want it, right? It's 1 over 1 plus x squared. I have 2x over 1 plus x squared. Okay, so some of you might think then, okay, no big deal. We've sort of had this issue before. Let's just fix it. Let's fix it by, doing a times 1 over 2x. And now, wouldn't that cancel when I do the derivative? And the answer is no, because now you've created what would be really almost an impossible thing to find the antiderivative of. Because now, if you'll notice, you've got a multiplication here. And so, what the heck is going to be the, the derivative of this? If you check it now, we have to do the product rule. And so, if this is the right derivative, then if this is the right antiderivative, right? If this is the antiderivative of that, when I take the derivative, I'm going to get the 1 over 1 plus x squared times 2x, so that's the derivative first, times the second. We look like we're doing pretty good. Now it's right, but then we got the other half of the product rule, which says plus, and then this times the derivative of that, and so we're not going to come anywhere close to this. So anyway, that's why it doesn't work. And that's why we're going to use our calculator. Technically, the answer to the question is, what's the antiderivative of this? It's actually going to be arctangent, but we're not going to get into that right now. So I'm going to stop this video because it's way too long as it is.